like a grayscale image. So if you have a RGB image, you have three matrices. So the convolution step that I showed before. So we have this is like the image represented here only by zeros and ones, and this is the filter. So it's some matrix that you are going to make the convolution with the image. So the convolution step, you have let me go back and move forward. Okay. So you have the filter being shifted in the image. So you multiply each element and then you sum the result, and then you put the result in a new image that we call a feature. Okay? So this is the convolution. So you can, for example, make the convolution between this image, like an animal, and some standard filters, for example, identity or edge detection, sharpen, blur, Gaussian blur. So this is the feature, the convolved image. Okay? This is another example. So the filter can also be an image. For example, here I have two examples, one bar like to the left and one to the right, more or less. And then the feature, so the convolved image, will be more or less, I could say, how likely is to find this kind of shape in this image. Okay? So, for example, if you have a filter, which is a circle, and you want to make face detection. So our face, you have like, the shape of our face is more or less a circle, then you have our eyes and our mouth and the holes of your nose. So you will have a strong convolved image if you use a filter of a circle, then a line. We don't have many lines, straight lines on your face, in our face. Okay? And then after doing the convolution, you do the rectification, as I said, which is only like change the negative values to 0. It's really easy. But why do we do that? Because of the next phase, which is the pooling. The pooling is when we change the image into a smaller one. So we can do this by, for example, in this example, you have this is like the convolved image, or the feature map, as we call it. And then we pick 4 elements, like a square, and then we choose the max value of this 4. And then we position this in a new image. For example, this example is max, but it can be a sum or an average, for example. Then you have a smaller image. So as I said, I showed here. So you can do the convolution, then a pooling, and then you can make a convolution again with this pooled image. So, for example, this one, we can make a new convolution with a new filter, and then a new pooling. Of course, not going to pool anything here because we have a 2x2 matrix, but usually have big images, and yeah. And then we don't want to use huge images in the neural network. So this is an example. So this is the image that I showed you, the convolved image. And then you do the pooling. This is an example of the pooling using the max values of each piece of the image. And this is an example of doing the pooling at the sum of square, many squares of the image. Okay? So these steps that I showed you is only for finding the features. Okay? So these features now, they have to go in the classification phase, which is the neural network itself. So this is neural network, multi-layer perceptron. So we have the input. So for example, you get this pooling image. So this is a 2x2 matrix. So for using it as an input of the neural network, you have to make it as a vector. So you only place the second line by the side of the first one and so on. So you have a huge vector. Because then this vector will go here as the input of the neural network, okay? So each element here is one pixel of this pulled image, okay? And then you have the neural network. It's a long time to explain, but this is it's a sum of each input multiplied by a certain weight. And then you also have a bias here to sum. And then you get this output from this sum and pass by a activation function. And then the output of the activation function is the input of the next layer. So you do the same, you sum all these outputs multiplied by this weight, and then you have also the bias in the sum. And then at the end, you have the likelihood of each class that you are trying to classify the objects, okay? So this is in this phase. After we extract the features of the image with the convolution and the pooling, then we use it as the inputs of the neural network. So the difference between the convolutional neural network and the ordinary or the old-fashioned neural network for images is that before the convolutional neural networks, the inputs here, the features of the neural networks were, like, for example, the average of the intensity of the image, for example, or distribution of the frequency. So we use it to do a Fourier transform, or you have the histogram. So this kind of elements, information, were used in the neural networks. But with the convolution now neural networks, we have these filters, and then we extract more information from the images, and this is very useful to classify them. So here is an example. So we have a car, and then I don't know which filters were used in this example, but you have the car, and then you have the convolution, and this is like the feature map. Then you do the rectification, and then another convolution, another rectification, then a pooling. You see, you can have many, many steps. And at the end, you have the last pooling, and then you use these features as inputs and on the fully connected neural network. So in this neural network. Okay, and then you have the probability of this being a car, or a truck, an airplane, a ship, or a horse, for example. With numbers, I have another example here. It's not really good, this image, but you have the input. So this is an 8, and then you have the convolution, and then the pooling, and then another convolution. And for us, like humans, we cannot classify anything looking at this second convolution layer. But after doing the pooling and making all these images of this pooling layer number 2 into a big vector, then you put it into the neural network, and at the end it's super small here, but this is like the digits from 0 to 9. So you then have how likely is this input image to be a 0 or a 1 or a 2 and blah blah, or an 8. So it's really likely to be an 8. So we then decide to classify as an 8. So some examples. Here is a paper about to count vehicles passing by a street. So the authors are using this fast a region convolutional neural network. So this region-based convolutional neural network is used to build the bounding boxes around the objects. So, and then you can classify. Because if you have only this image as an input, you have like many cars and a bus, so you can't classify. So again, an important step is to extract the box, like the window where the object is. Okay? So yeah, that's it, this example. This, so as you see, these images are taken horizontally, so in the level of the objects. But usually, as we are talking here about UAVs, we are talking about aerial images, so we call vertical images. So for example, this is one paper about scene understanding with the UAV. So we have 3,864 images, 4 classes: building, ground, road, and tree. And then you can classify and extract what is a tree, what is a ground, what is a building, what is a road, okay, with the UAV and convolutional neural networks, of course. This is another example, but not really, it's not like what we do with the UAVs, but it's important because it's a grayscale image. So as we are working with infrared, this X-ray, so not infrared, but it's also grayscale, so it's important work to use as a reference. So this is for image retrieval. So what is that? It's, for example, you have a huge data set of X-ray images, and you have one one image of a hand, for example, an X-ray image of a hand. So image retrieval is to find in a huge data set which images have this hand. So we have an input image, and then you find in a big data set every image that has this input image or something related to that. Okay? This one is also with UAVs, so low-cost UAVs to classify animals in Africa, in Namibia. Okay? So they have 654 RGB images, and they had to label the animals first, and then they did some kind of automatical labeling, but then they had to make some fine-tuning with human supervision to find some animals that the automatic labeling couldn't find. Okay? So also aerial images, that's interesting. They use this also this fast RCNN, which is the region-based. It's a really famous convolutional neural networks for finding bounding boxes, like the region, the window where the object is. This is another one using UAVs after avalanches. So, but with electrical optical camera. So this is just an example of, this is we didn't find any human here, so we didn't have any human, so it was a negative, a corrected negative classification, and here positive one. Here, I don't know if you can see this yellow small box, so the classifier is saying that there is a body here, but there isn't, so it's a false positive, okay? And here is a false negative, because there is a person here, but the neural network couldn't find. And also, for example, every time we're working with neural networks, we have the probability of being something, of having something. So you can also change this bias. So for example, if you are in an avalanche scenario, you want to take a look, even if the probability is low, to have a person there. So we want to check. So you can change this bias and, for example, I want to see all the images with 10% of probability, because then it's important to check if there's a body there. Okay. This other example is from aerial images. So you have three classes: road, building, and background. I also like this this paper. It's really nice that you can find all the roads and where you have buildings and where you have nothing or just ground. Okay. So again, when you have, for example, this image, this as an input, you have to extract many small regions, like squares here, and then you classify, and then you will build the whole map. But the work to classify all the roads and buildings and the ground, you have to take a small little piece of the image and then classify and make it for the whole image. Okay? This is more likely what we are doing. So we have mammals and some pictures from the ocean with these mammals, and then you count these mammals. So this is the paper that mostly relates to our work, classifying boats and buoys and people in the ocean. Okay. So to find the square, the box around the mammal, they did the following. For each pixel of the image, they calculated the likelihood, the probability of it being a center of a square of a mammal. So it's a crazy work to get these boxes and then classifying. Actually, the classification with the convolutional neural network is like the easy step, in my opinion, at least. I think that the difficult is to find the box around the object. Okay, especially here that we have the mammal, but you see that the color is similar to the color of like the sand on the water and so on. Okay, now infrared images. So it's difficult to find many works on convolutional neural networks with infrared images, and especially aerial images. So it's really something difficult to find. So this work is to classify people using infrared images. So we have fuzzy C-means to find the candidates, and then you have the convolutional neural network to classify these blobs, these regions, if it is a person or not. So they used a public data set with 8,000 pedestrians and 8,000 pictures without pedestrians. So about our data set, finally. So this is an example of the electrical optical image. So you see that they are totally different. It's really difficult to extract the box around the boat, because this is just like a shadow. It's difficult to say that this is a boat, you know. And in this boat, this is easier. Then now we are working on the infrared images, and then we are going to attack the RGB images. So for now we have the infrared images. So you see this is an infrared image. Have the boat here. This is probably a pallet, and there is a person swimming somewhere. I know where the person is here, but you cannot see. So this is how the infrared image looks like. So you see the boat, and then the pallet, and this is the person, and somewhere here a boy, I don't know. As Christopher showed, so we have the extraction using the blobs, so it's really easy in the infrared image. So we can just make some blur on the background, and then we can find you have these white blobs, and then you can find the objects easily. So you can imagine it that in this case it will be really difficult to do the same. So then probably we don't know yet how we're gonna work on this, but probably we use this pre-trained convolutional neural network. So we have available like many pre-trained convolutional neural networks that we can then use to extract the objects or the region where the objects are. So like convolutional neural networks trained with thousands and thousands of samples. Okay, so we are going to do, we have 4 classes, as I said, like a boat, pallet, boy, and person. We have different boats because, of course, when the UAV was flying, many boats were crossing and so on. We are going to have k-fold cross-validation. So what is this? Like we have our data set, and then we will separate a piece of this data set for test and use the rest for training, and then we change which fold will be used for testing and so on, and then we will have the average. This is to have the true performance of the neural network. Because if we only pick it randomly, the samples to use for the testing and for the training of the neural networks, you can, for example, the random choice can be good for the neural network, so you have accuracy that's not really true. So we do this cross-validation, and we are going to train the neural network with the early stopping validation curve. So you have the error, and then you are training the neural network, and you also use a piece of the training data set as a validation data set. So when the curve of the validation starts to, stops to converge, then you stop the training here. So this is a good method for stopping the training of the neural network. So yeah, that's it. Thank you. Have any question? Yes? Yeah, okay. Actually, this, let me go to this slide. So the convolutional neural network is like everything here, so all the steps. This step of the classification is where the ordinary neural network is. But all this feature extraction is considered part of the convolutional neural network. Just like to clarify that. Yeah. Yeah, you mean in the neural network itself, the fully connected layer. So yeah, and I forgot to mention something also important, that in this example, I don't have that, but also as Christopher works with this georeferencing of the image and so on, he can also estimate the size of the images. So this is the size of the objects, sorry. So this is also a good feature. So we can, for example, use the size as an input directly on the classification phase. So as an input here, we can use the size also, but this is only observation. Now we answer your question. So we are using only one hidden layer, okay? Activation function, we are still checking, but the master student is making many simulations. But we have the linear, also sigmoid, and also this, acho que é Tansig, is the one like this. What is a sigmoid? Yeah. Yeah. So these are the activation functions that we are using. And as I said, it's a fully connected layer. So all the inputs are connected to all the sums and so on. So we are still like making the simulations of, but I can tell you that it's only one hidden layer. So it's a multi-layer perceptron feed-forward neural network. Okay? Yeah? Alois? And then Andre? Okay, yeah, good question. First, Christopher, can you ask about the size of the data set? I'm not sure. 12,000 images? Okay, so kind of almost 2,000, 2,000 images with the objects, okay? And about your second question, now we are using just, I think, I'm not sure, but pretty sure it's backpropagation to train the neural networks. But for example, in my, you asked something that I worked a lot with, because in my master's thesis was about tuning the neural network with particle swarm optimization. So I was using an algorithm to find the best architecture of the neural network. So, but in this case, in convolutional neural networks, usually they use this fully connected neural network. So we don't really do any optimization on the architecture of the neural network, but only like the bias and the weights and so on. But then we're using the standard backpropagation algorithm that you propagate the you guess the weights, and then you calculate the error, and then you backpropagate the error, and then you change the weights. Yeah. Yeah. I'm telling the others. Yeah, it's like a heuristic. We just like try and this is what is done. Okay, Andres? Oh yeah, so in the Avalanche paper they are using pre-trained CNN to detect the objects, but then they use a vector machine to classify if it's a person or not. What? What's it? Okay. No. Yeah, in our dataset, we will try to use the convolutional neural network to classify at all. We're not using, for example, spot vector machine or anything. So we'll try with only the convolutional neural networks, and then we will see if we try other solutions. Yeah, and also because we have no idea how it will perform with the infrared images. So we don't know, because you see like these infrared images, and they are not really high resolution, and they're a bit crazy to, at least for us, like for humans, to see this and say, oh, this is a palette, this is a person. They're really complicated. But we hope that the computer will make it. Yeah. Any other question? Yeah?
So your application concerns search and rescue.
Yeah. Yeah, no, but for example, in the, I forgot also to mention, because our idea is to use both the electrical optical images and the infrared images in a complementary way. But in the mission where we got the data set, the flights with the infrared images weren't the same flights with the electrical optical images. So unfortunately, we can't use the two images as inputs. But we will work on the electrical optical dataset and also the infrared dataset, and we will try in the future to merge, for example, make some kind of cross probability multiplication to try to use both information. But in the best approach is to have both electrical, optical, and infrared camera in the payload, and then classify using that. And then we can avoid, for example, the waves and so on with the infrared image, and then they can complement each other. So we think we will avoid this kind of problem using the two kind of images. So this is the what we think, but we will see. Margarida? Yeah, this is more or less what we are going to do. So, but we are. I forgot we talked a lot about this, but now I didn't prepare anything about this part in the presentation. Then it has been like 1 month since I last talked about it. But we have a solution like to train one network with the infrared and another one with the electrical optical, and then we are going to do some how can I say, like cross multiplication with all the outputs, and then see if we can use, for example, the boat. Yeah, we have an image with a boat, a pallet, a boy, and a person. So we extract the boat window, and then we classify. And then we have the likelihood of being a boat, a pallet, a person, and so on in the electrical optical image, and the same with the infrared image. So we can just, for example, multiply all the probabilities of the output of the infrared and the output of the EO, and see in this as a new probability of being. And then we will see, this is the way we found to use both data sets. Okay, but then like in the through a payload and through application, a practical application, then we have the same image, exactly the same image. So the best is to use one neural network with both inputs. It's almost like two features, you know. Yeah. Yeah. Oh yeah, that's a good question. So again, the classification is real time, is easy. The problem is the object extraction, but there are many good available algorithms as the FAST and the faster R, C, and N, and they can achieve a real-time object extraction now. So this is what we are going to use probably. And this algorithm to extract from the infrared is real-time. It's really easy. It's just blurring and then blobs, and then you extract the window. And then the classification is easy because the training is what takes time. The classification is just like, just sums and multiplications. So this is, if you have an image here and you want to classify, this is not costly computationally. Yeah, this is part of the path planning. So we have this cooperative search. So it's the other part of this project. So we have many UAVs flying, and then, for example, if one UAV finds something, or at least you have a probability of finding something, the other UAVs will fly in this region to update and to get more data. This is part of the path planning system. Yeah. Okay. Okay. Huh? Which one? Our data set? This one? Okay. Here to extract so yeah, can Christopher talk? Background extraction, yeah. So you only make you blur you don't blur no? Ah, okay, yeah, sorry.
Since you're doing external Gaussian moving image, are you just kind of subtracting the dark frame for the image and filtering out all the infrared camera imperfections?
Yeah, so this is basically models the background as a mixture of Gaussians. And it moves so well even though the camera is in the lane. Because most of the noise and stuff like that actually comes from the camera itself. So it's very uniform actually based on the image doesn't really take effect.
And he also uses the georeferencing of the images. So he is also kind of tracking the object to do the labeling and the extraction of the boxes. So because he knows that the boat is here, so it will be in the next image, it will be close to where it was. So, right, Christopher? You're doing something like that. So yeah, also doing some georeferencing.
What I wanted to follow up with was, if your point was about the environmental conditions, you're only going to see bright features, right?
Bright picture.
Bright features are all you're going to see. You have to have a bright feature in the background, right?
It's like a sky blue, like a sky blue.
You need a bright chip. You need something that has a strong density.
Yeah, this is infrared. So
Right.
Yeah.
So in those kind of conditions, say the pal's going to look it's going to be the same temperature. If it's going to be washed, it's going to be submerged. Same as
I see.
the cursor potentially as well, especially as blurry as you're looking in that.
I see.
Whereas this may be a pretty common condition.
yeah, so that's the hope for using electro optical, for example. You can see a little bit down in the water and something.
These are different voice characteristics.
Yeah. Yeah. So I mean, I understand. Maybe we should, for example, have the images, the data set in a strong weather condition, and then using the neural network. It would be the best for sure. Yeah. And then you can fly in a strong weather condition, and then you get all the images, and then we let the computer to do the training and everything, extract everything.
Right, so how long does it take to run through the data set with this algorithm to do this?
Yeah. For the extraction. Yeah. Okay. Other questions? Oh, then thank you very much.